Hello, this is take 2 of the video. I already started talking and then realized that my video had stopped. So, take 2. So this is the last week of Learn at Home. We're going to finish up next Monday with a Unit 5 video assessment, but this is the week where we're going to wrap up all the new material, okay? We're going to have a review on Friday of this week. So the actual last day of new material will be Wednesday. Okay, so 5.3 day 2 asks us to focus on these goals. Goal number 1, determine the probability of a specific outcome using the binomial probability distribution formula. Okay, so that distribution formula we already did here, right? So this is the probability, the binomial probability distribution formula. Okay, that's what it is. Okay, we're going to determine the probability of at least a specific outcome using the binomial probability distribution formula and determine the expected value of a binomial experiment. So our first goal is really a revisiting of day 1 material, and then the other 2 goals will be more for day 2, which is today. Okay. All right. So recall, given a binomial distribution of a random discrete variable x, the probability of a specific outcome is given by the probability of x taking on a k value. Now notice the only difference here for this formula to this one is that now they're representing this value in the bracket as not as n, but now, or sorry, not as x, but now as k, okay? So this formula, although it looks new, okay, it's just like day 2, or sorry, just like day 1 in 5.3, only x, little x, is now k. And for your purposes, you might find that a little easier. It is difficult to distinguish between capital X and lowercase x, right? All right, so we said that capital X was the discrete random variable. So in our situation on day 1, we talked about the discrete random variable representing the coin toss and the possible outcomes of the coin toss. So k in our situation is now what x used to be, okay? And k is the number of successes. So if we have said that in day 1 we wanted to know the probability of flipping the coin and getting heads, then we would deem our success as flipping and getting heads, okay? So n was representing the number of trials, so that's still true from day 1, and p is the probability of successes, and that's still true for day 1. So the only thing that's different now is this, right? It used to be little x in day 1. Okay, it was little x. All right. The thing that's new is this expected value idea. So the expected value or expected number of k successes is given by this crazy looking formula. Okay, very, very complicated. There's two versions of it. So your expected value, this is one way of looking at it. Okay, so this is method 1. Okay, and this is another method 2. Okay, so it says that the E at x is the expected value or expected number of successes for capital X. Okay, so the number of times that I would successfully flip a coin to get heads for this discrete random variable. Okay, so n was the number of trials and p is the probability of success on each trial. So if we look at this formula and we say, well, it's really complicated, we can look at it in a couple of ways. So let's uncomplicate it. So method number 1, okay? So if I took my sheet here and I said that my little x was the number of heads, okay, and so little x was the number of heads. So here I could have 0 heads, 1 heads, 2 heads, and 3 heads, okay? So I'm talking about the expected number. So and then my probability of little x, I was told the probability of getting 0 heads was 1 out of 8. And the probability of getting just the 1 head out of 3 coin tosses was 3 out of 8. And the probability of getting the 2 heads out of 3 coin tosses was 3 out of 8. And the probability of giving 3 heads out of 3 coin tosses was 1 out of 8. Okay? Now, if I want to find the expected value, okay, so what is the expected number of heads in 3 coin tosses? I could say that that's equal to multiplying the value of little x times its probability. And this is what it's saying. So take the value of little x. So this is x1, this is x2, this is x3, and this is x4. Okay? So my expected value of getting heads is multiply x1 to the probability where x is equal to x1, okay? And add that to x2 and multiply that to the probability of where x is x2, okay? And then add that to x3. So when we get this value here, okay, multiply that to the probability of when x is x3, okay, and then add it to x4 and multiply that to the probability when the discrete random variable is equal to x4. Now, what does that mean? Because that probably just still doesn't make any kind of sense. Well, all that means is take this number and multiply it, okay? So you'd get multiplication here, multiplication here, multiplication here. Okay, so what is that equal to? Well, it's 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. So literally it's all of these values just written here, right? Okay, so I'm still trying to figure out what the expected value. So what is the expected number of coins that will turn up heads in a 3 coin toss? Okay, that's my question. Okay, so 0 times any number is 0. 1 times 3/8 is 3/8. 2 times 3, that's over 1. So 2 times 3 is 6/8. And 3 times 1/8, 3 is over 1. So 3 times 1 is 3 over 8. So we've got 0 plus 3 plus 6 plus 3 is, what does that give me? 9, 10, 11, 12 over 8. And what does that get me? Well, that gives me 12 divided by 8, which gives me 1.5. So that means, okay, so I can expect to get 1.5 heads from 3 coin tosses. And you say, huh, that actually makes sense. And that's what I want you to say, right? Now, what if I did method 2? Okay, so method 2 for expected value. Okay, so expected value is this formula here, n times p. Well, there were three coin tosses, and the probability of getting heads in 1 coin toss was 1/2. So 3 coin tosses times the probability of getting a head on a coin toss, that's over 1. So 3 times 1 is 3. 1 times 2 is 2. What's 3 divided by 2? Well, you know it just as well as I do. 1.5. Okay, and that's method 2. So I can expect to get 1.5 heads from 3 coin tosses. Is that the exact same? Yes, absolutely, that is. So that's the same as that. So method 1 and method 2 are used depending on what values we have and what information we have available to us, okay? Alrighty. Okay, so example 1. Recall, the discrete random variable x is defined by tossing a coin 3 times, and the success was defined by getting heads, right? So determine the expected number of heads in 3 trials. Well, that was silly of me because I just did it. So C method 1 and method 2 above and to the right. Okay, therefore the expected number of heads is 1.5 heads in 3 coin tosses. So maybe I will get it's not going to work. Okay, so that there and that there, method 1 and the answer, and then method 2 and the answer, okay? Alrighty, so recall the following probabilities that were determined in the previous lesson, so that's day 1, okay? So if we had the probability of the discrete random variable being 0 heads, we said that that was 1/8. Okay, we said the probability where the discrete random variable was 1 head, we said that was 3/8. We said that when the discrete random variable was 2 heads, it was 3/8 again. And then we said when the discrete random variable was equal to 3 heads, it was 1/8. Okay. So determine the probability that you would have at least 1 head. So at least 1 head means 1 head. It also means 2 heads, but it also means 3 heads, right? So my probability of at least 3 heads is equal to the probability of 1 head plus the probability of 2 heads plus the probability of 3 heads. Now, I already have these values here, so I'm just going to sub them in. So that was 3/8 plus 3/8. Oops. Plus 1/8. Okay, so 3 plus 3 is 6 plus 1 is 7/8. Okay, so that's one way of looking at it. But if we want to look at note number 2 to find the probability of at least k successes using the complement, okay, using the complement, it means that if I want to know the probability where the discrete random variable is at least or greater than or equal to k, where k is 1 head, then it would be 1 minus all of the probabilities that did not include at least 1 head. Okay, so let's do that. So let's try finding the probability of at least 1 head, okay, is equal to 1 minus what's not included. So we already said that at least one head would be the probability of one head. It would be the probability of 2 heads. It would also be the probability of 3 heads. So what is outside of that probability? Well, it's the probability of 0 heads. So the complement, using the complement, the probability of getting at least one head is 1 minus the probability of getting 0 heads. Okay, so what is that? Well, that's 1 minus the probability of one head would be 1/8. Well, 1 is 8 over 8 minus 1 over 8, which equals 7/8. Okay, so these are the same. And you say, why do you keep telling us two methods, right? So this is method one for C, okay, for question C. And this is method 2 for question C. Let's just say C, okay? What I'm trying to do is build your comfort level, okay, with the questions, right? So if you can see how they actually really work, then you're going to believe in what you're doing and you're going to have a little bit of more flexibility, okay? All right, let's get going on to the next page. All right, so a bag contains yellow and blue marbles. Hopefully this sounds familiar back from Unit 4. There is a 0.8 probability of selecting a blue marble. So instead of telling you how many yellow and blue marbles there are, they just convert the probability for you, right? So if we were to put this question back in Unit 4, then hypothetically I could say, well, there would be 8 blue marbles and 2 yellow marbles because 8 out of 10, right, converts to a decimal of 0.8. Okay, so this kind of question in Unit 5 just already does the probability most times for you. Okay, sometimes it doesn't, but it does here. There is a 0.8 probability of selecting a blue marble. A marble is withdrawn 4 times. Each time the marble that is withdrawn is replaced. That's very important because we don't want our trials to influence each other. Therefore, the probabilities for each trial stays the same. Now, if we didn't make a big deal of it, it might not be, neither here nor there. But the fact that this information said that the trials are independent of each other, okay? It means that what I do by selecting my first marble, okay, that should not influence what I select in my second trial, okay? So every time I'm drawing at a marble in this example, I should have the same probability of 0.8 getting a blue marble. Okay, determine the probability that you withdraw a blue marble 3 times. Okay, so we want to know a couple of things. Is this a Bernoulli trial, and can we use the formula from day 1? And the answer would be yes. And the reason is, if it's replaced, okay, it's a Bernoulli trial. Or Bernoulli trial, okay? So since it's a Bernoulli trial, okay, therefore we're going to use the formula. So probability of x equaling k, where k is a success, is equal to n choose k times the probability of being successful, right? So over here, right? Times the probability of success to the power of k successes, okay? times 1 minus probability of success to the power of n minus k. Okay, so this is the important part. N is still the total number of trials. So I'm withdrawing 4 times. That's my n value. Okay, so n is 4 trials. Okay, my k is how many times do I want to be successful. I'm deeming success a blue marble, and I'm doing that 3 times. So k is 3 successful. Let's use the word successful. 3 successful withdrawals of a blue marble.